Okay, it is time to start here. Just going over the people I don't see: Chad, Bridget, Reagan, Diksha, Zach, and Tori. Okay, today is just a review. I've been trying to get all the grades up as much as I can. There are the 2 labs that aren't graded yet, so those will still be there to change. Attendance bonuses will be final after today's class. I've put everybody in who already had it earned, whether they were here or not already. You might notice that's why some people are missing here. They've already got their attendance bonus, and with the spreadsheet you can see, what you need in the final. So as soon as those lab grades are to me, I'll update them, but since I'm waiting on Erica, I can't just, make them up right now, so I'm sorry about not having those available. Any questions about the grades?
So you just have 2 labs left?
There are 2 labs left to be graded, yeah. Everything else is recorded except for today's attendance.
Have you dropped the 10 lowest contract?
Yes.
You did?
Yeah.
What's the lowest C?
69.5%. I don't give C minuses on a philosophical difference with the college. I think a C minus should be a passing grade, but if it's required for a major, it's not considered passing grade. And so I just don't give them. That way we don't have to disagree on a low pass. It's a C then. Okay, so when is our final exam? It is a 10:30 class. So that means it's Tuesday from 1 to 3 p.m. So we will meet here for the exam on Tuesday at 1. So it's a little before the normal time for lecture. You don't have to come to the lab or to the final exam if you're happy with your score. The final exam can't lower your grade, it can only raise your grade because you have, out of the 5 exams, only the top 4 are going to be counted toward your grade. So right now, all 4 exams are being counted toward your grade. And after the final exam, then you'll be taking the lowest one and kicking it out. Question?
I have a question. Like for the poster scores, was everyone equally weighted, or was yours like one versus class?
Ken's and mine were weighted equal with the rest of you combined.
Okay.
So it was 50% Ken and me, and 50% everyone else.
Okay, I just wondered.
Okay, what will the test be like? Just like all the others. It will have probably about 10 questions. It'll be cumulative over the entire semester, but about half of it will be from material since the last exam, and the other half on material from the rest of the semester. So it's putting a big emphasis on the last few weeks, but it's cumulative over everything. Just like before, it'll be a mixture of conceptual questions and problems you have to work out. Make sure that you give your reasons for how you solve the problem, not just, I put the numbers into the equation. And, same rules we've had all the way through. Just want to emphasize for the final exam. There will be 2 Physics 252 specific questions, one from 31 to 33, and one from before that. So any questions about the design there of the exam? Yeah.
There will be 8 questions for those who are not here.
Well, you will have 8 questions in common with the 152 students, and then you'll have 2 252 specific, and they'll have 2 additional 152 specific. So you all have the same number of questions. I'm coming back here because it's a distance away. Okay, so now just reviewing over the topics that we've covered. This is just highlights of what we've covered this semester. This is not cumulative over first semester. While force is still in play, energy is still in play second semester, we're not going back to first semester, so we're not going to have like an inclined plane problem or something like that. So, know your history of electric charge knowledge, right? Things like how Ben Franklin randomly decided to make electrons negative charge, and the experiments that showed that there were 2 types of charges. not just one type of charge like you have with mass. The key difference between conductors and insulators, they both have electrons, right? And you can add electrons or take electrons off of both. So what makes the difference? If it's a conductor, the electrons can move with a fairly small amount of energy required. If it's a superconductor, it's a much smaller amount of energy required to make the move. Okay, Coulomb's law, that's our law that gives us force. As always, you'll have the equations. What is R in that equation? We mistake it for radius. That's why I asked the question. It's the distance between the centers of the two objects, assuming spherical symmetry. This is for point charges specifically, and so it'd be from the center of one point to the center of the other point, which you don't need to find a center for a point because there's no size to a point. Know what electric fields are and how they're useful. Right? The electric field is defined as the electric force divided by charge. Just like the gravitational field is the gravitational force divided by the gravitational charge, mass. So make sure you understand what the electric field and how it's useful. So you can take problems. I have a particle, it's in this electric field, what's the force? Boom, force is electric field times charge. That's the reason we have it. It makes life simple for us. Gauss's law. Remember Gauss's law, one of the more complicated things we've done. The electric flux is equal to charge enclosed over epsilon 0, where the electric flux is a calculation of how much electric field is coming out of a closed surface. So it's sum of electric field dotted to area over a closed surface. So you have to have a closed surface, no gaps. The whole idea that Gauss had was if I can measure how much electric field strength is coming out of a region, I can tell you how much charge is enclosed. That was the point of it. And so we can go through and do calculations and use Gauss's law to find charge enclosed or to find electric field strength. So we did some simple applications like using Gauss's law to find electric field for a point charge, or using Coulomb's law to find electric field for a point charge, and we found that they came up with the same equation. For Gauss's law, we had to use situations where we had some useful symmetries, or it becomes difficult to do the calculations. Electric potential. What is the more common name for electric potential? Voltage, right. It's kind of useful to know that because the words are used interchangeably, and if you think they're two different things, well, then that's going to be to your detriment. What about electric potential compared to electric potential energy? We know what potential energy is, so what does it mean if we take away the word energy? Okay, the electric potential is voltage. Well, I'll write the equation for it because that makes it very clear. The change in electric potential is equal to the change in electric potential energy, actually, our textbook PE, per unit charge. So the electric potential is the potential energy per charge. And so if you know the electric potential difference, you know the potential energy difference for a given charge going from point A to point B. That's very useful to us because then we do something like I have a grid and I put a charge in between there, and I have voltages, so I have a voltage difference, so I'll say this is V1 and V2. Then the potential energy difference between those two is equal to Q times the voltage difference between the two. And so I can figure out how much potential energy changes going from one side to the other. Well, if I have a charge and the only force acting on is the electric force and it makes it zoom across here, what happens to the potential energy when the potential energy is removed? We had two fundamental types of mechanical energy. If you take it out of potential, where does it have to go? What do you say?
Did you say what happens to the potential energy once the potential energy is removed?
Yeah. Yeah. So where does it go? It goes into kinetic. So you start with this potential energy, you transfer that potential energy to kinetic energy. So we'll have the change in total energy is equal to change in kinetic energy plus change in potential energy. If the change in energy is 0, then that means your change in kinetic energy is equal to minus the change in potential energy. So the potential energy moved into kinetic. To that end, we have a very nifty unit for kinetic and potential energy. Instead of joules, what did we start using? The electron volt. That's right, the electron volt, because I have charge times change in voltage. If I have an electron, we usually have charges of 1 electron, 2 electrons, and it goes through a voltage difference of, 2,500 volts. I just say, well, if it was an electron that went through 2,500 volts, then it picked up kinetic energy of 2,500 electron volts. And so I didn't even have to whip out a calculator, didn't have to think. Just knowing what an electron volt is allowed me to instantly put a number to the kinetic energy there. Capacitors. Capacitors, devices that store a charge separation. And if I have a charge separation, then that means I'm going to have an electric field. Electric field lines always go out of positive and into negative. And so you can think of a capacitor as either storing a charge separation or storing energy in the form of an electric field. Basic relation, Q is equal to VC, that is this Q here. We don't say the plus Q and minus Q, we just call it Q, is equal to the voltage difference between the two plates multiplied by the capacitance. So a simple relationship, again, between the energy per charge, the total amount of charge, and that is the capacitance. In fact, capacitance is defined as that. Make sure you understand the physical construction of capacitors, that it is kappa epsilon 0 A over D, where A is the area of the plate and D is the separation between the plates. Kappa is a dielectric strength. If kappa is 1, it's vacuum. If you have something like mica, kappa is going to be higher than 1, which means it increases the capacitance. In a practical sense, we use capacitors a lot of different ways. What was the way that you used it? Let's see. Jaron, who else is in your group? Helena? And Cassie. Okay. The three of them used capacitors. What did they use those capacitors for? For what? Okay, for storing a charge. They charged them up. They put a whole bunch of electrons on there and had it hold all of those electrons. So where were the electrons originally? Well, your batteries took them from one side of the capacitors and moved them to the other side, right? Because the batteries don't make or destroy electrons. They just give them energy. And so the battery slowly moved electrons from one side to the other. And then after you had as many as the batteries could move, as defined by this equation right here, then you dumped all of those electrons in a very short time through your coil. And so there was a lot of energy stored there. You dumped all that energy very rapidly. So that's one common usage. Another common usage is to smooth out rippling currents. If you want to have a constant direct current voltage, use a capacitor to smooth that out. Or when we get to AC circuits, we use them a lot in filters. Okay, talking about electric circuits, we had Ohm's law, V equals IR. A very simple law that doesn't work for every material, but it relates the energy per charge, electric potential or voltage, across an object to the rate at which charge goes through it. And R is that, once again, R is just defined as the voltage difference divided by the current. So Ohm's law gives you a lot of power in working with electric circuits. Such a simple law, electric circuits should be really simple. Oftentimes students don't find them simple because they're a lot like puzzles. You have to figure out how the pieces go together. But the basic rules are simple like puzzles. It's figuring out how the pieces go together that makes the difficulty. How does the body respond to electricity? Hey, what? It doesn't like it. Well, it doesn't like it at certain quantities. Our bodies run on electricity, right? If there's no electricity, my heart doesn't beat, my muscles don't move, my brain doesn't think, my nerves don't, well, of course, the nerves don't pass the information. So our bodies run on electricity, but because they run on electricity, if you put your own electricity there, you can interfere with the way the body works. So we learned you can feel a buzz at as low as 1 milliamp. That is current. Current flowing into the body, you feel a buzz about 1 milliamp or so. You get up to about 10 milliamps and it'll start to cause muscles to contract involuntarily. That is, instead of your brain sending a voltage to make your muscles contract, you have put some external thing that's making your muscles contract. So you're not controlling it the same way. Now you could make a robot. I could take Lindsay and put these little pads all over her body, and then I could make her do whatever I wanted by controlling voltages. But that wouldn't be very nice, would it? Your dad's a physical therapist, right? So he does that to people, right? But it is voluntary, and it's to help them recover usage, not, I'm going to make you get up and go to the fridge. Yeah, no. Okay. If you get up to about 50 to 70 milliamps going across the heart, that's enough to cause the heart muscle to start behaving in an incorrect fashion. You overcome the voltages that are normally going across the heart, and of course that's potentially fatal. You get up even higher, and instead of just overcoming the voltage in the heart, you can just stop the heart. You just depolarize the entire muscle. That's what we do to try to resuscitate somebody who is in certain shockable rhythms. We give them a nice shock to stop the heart in hopes that then the heart will start up on its own. But there's only certain rhythms where that can work. Some rhythms, it's not going to restart. And so, well, no point in just stopping the heart for it to not restart. All right, make sure that you can calculate electric power. Very simple. Once again, power is just the energy per charge times the charge per second. That is the energy per time. So power is voltage times current. AC and DC. Why do we use AC in our homes? It's easier to transport, and especially it's easier to change the voltages up and down. That's a big part of why it's easier to transport. That's why we use AC. Why do we use DC in our smartphones? In my iPhone, why is it using DC? Because it's a battery. Batteries produce a constant voltage, a constant current, not an alternating or oscillating one. And so since we're using batteries because we want to charge and store the energy in a battery in a chemical reaction, that's why we use DC for our phones and calculators and whatnot. Okay, some solving circuits. Remember Kirchhoff's laws. We had the two laws. Kirchhoff's current law that basically says charge can't be created or destroyed. So any charge that comes into a node where two or more elements connect, has to leave the node. And the rate it comes in has to equal the rate it leaves. So current in equals current out. Very simple law. Kirchhoff's voltage law says we can't create or destroy energy. So if I start somewhere in a circuit and go all the way around and come back to where I started, I have to be back to the same energy. It's kind of like saying if I hike up a mountain and then come back down the mountain and get to the starting point, I have to be at the same elevation I started. That would be pretty obvious, wouldn't it? But that's what Kirchhoff's voltage law says. But those two laws give us equations that, combined with Ohm's law, allow us to solve any sophisticated circuit that contains just resistors and power supplies. So make sure you can do that. Just, oh, we didn't do that lab because, what was it, snow day? Yeah. So we only had that in class. Usually you have the experience of, having to solve them in lab where somebody's looking over show and can help you. Okay, voltage meters and current meters. Let's talk about internal resistances. What's the internal resistance like for a voltage meter? It's really high, which is what she was indicating. I wasn't ignoring you, just wanted to make sure other people answered too. Current meters, what's the resistance internal for a current meter like? An ammeter, as we call it. It's low. Why should they be different? An ammeter, you have to make the ammeter is measuring current. An ammeter, you have to make the current go through the meter. But you don't want the meter to cause significant differences in your measurement, and so you want a low resistance so it has a minimal impact. A voltmeter, you're measuring the difference between two locations, so you're putting it in parallel. In that case, you want a very high resistance so you don't have current flowing through it at an appreciable rate. So that's why they have those different resistances. Because of the low internal resistance of the ammeter, it's susceptible to damage if you put too big a current through it. The voltmeter, with its high internal resistance, you can put a really high voltage across it and it's unlikely to cause a problem because of that high resistance. Hence, we only worry about students damaging the ammeter portion. Magnetism. Woohoo! We learned a lot about magnetism. I learned some things about magnetism from our group with no representatives here. I did not know how the pinning worked. I told them I was going to rely on... Actually, were you in that group, Austin? Okay, awesome. I told them I was going to rely on them here because I don't have that much knowledge. And I did learn some things in their presentation, which was excellent. Yeah, no big deal. Hey, we knew it'd be excellent. So magnets, three types of magnetism: ferromagnetism, which is our strong magnetism; paramagnetism, a weak magnetism; diamagnetism, a repulsive magnetism instead of attractive. They have to do with quantum mechanics at the basic level of what makes them, so we didn't really get into that. But we did talk about ferromagnets, and a ferromagnetic material has these little domains in it, and each domain acts like a little magnet. And naturally, those little domains are usually just randomly oriented, so you have magnets pointing in all different directions. Well, if you add up the magnetic fields of magnets in all different directions, statistically, what's it going to add up to? 0 if they're randomly distributed. So typically a piece of iron, ferromagnetic material, it's called ferromagnetic because iron is strongly ferromagnetic. A typical ferromagnetic material has no magnetic behavior on its own. But if you can align those, it will have a strong magnetic behavior. So how do you align them? I did it in class. Okay, I used a strong external magnetic field to align them. And even when it's nice and cold, they will align and make it magnetic. If you heat it up to a temperature we call the Curie temperature, they're free to rotate and you'll make your strongest magnet. Then you cool it back down while still in the magnetic field and boom. So that's how we can make a permanent magnet versus a non-magnet, is by aligning them instead of letting them be randomly oriented. Magnets always come in dipoles. Di, of course, means two. So you always have two poles. The two poles we call a north and a south. And just like with charge, with its dipole, charge we called it a plus and a minus, the opposites attract and likes repel. And of course, there is that little bit of arcane knowledge. They decided to call it a north-seeking pole and a south-seeking pole. And so the north-seeking pole points towards the Earth's north pole. But since opposites attract, that means the north-seeking pole is actually pointing to a south magnetic pole. Hence, the Earth's north magnetic or north pole is the south magnetic. How's the Earth's magnetic field created? It's not like this. It is like what Jaron said. That's what it looks like, but how's it created? Well, I do believe God is what set things up, but I'm also going with Ann's. She's not saying get on with it. She's saying we have swirling conducting material in the Earth's core, we believe, that's making the Earth's magnetic field. How do we know? We don't. No one's been there. No one's observed it. But we can observe the magnetic field and the variations, and we can do computer models, and the result is what is predicted by the theory. That theory predicts what we actually have. So we believe the Earth's magnetic field is created by swirling charge. We learned that charge moving, that is a current, makes a magnetic field. Make sure you know your right-hand rules. On this page, I just said your right-hand rules. We had right-hand rules for the force of a charge moving in a magnetic field. Force equals QV cross B. Or for a current in a magnetic field, force equals IL cross B. But then we also had right-hand rules for the direction of the magnetic field when I have current going through a wire. Right, thumb in the direction of current, fingers wrap around the wire, the direction of the magnetic field. Or for the direction of the magnetic field in the middle of a solenoid, you wrap your fingers the direction the current's going, and the solenoid and your thumb points the direction of the magnetic field in the center. So we had three right-hand rules, because these two here, the cross product, are the same that we learned first semester, for using in magnetism. Electric motors. You remember the design of electric motor? You should. You have to have a coil. You put current through that coil, which creates a magnetic field for that coil. You put an external magnet, and you're going to have a torque between the two. A torque to make their magnetic fields align. And of course, once they're aligned, you have to have something to change the direction of the current in the coil so that it will go around another half turn. Otherwise, you have a stopping motor. Ampere's law. Ampere's law is the law that tells us about the magnetic field created by a current. Yeah, I'm trying to remember what that equation is. It was the circulation on a loop is equal to mu watt times the current enclosed by the loop. Really looks a lot like Gauss's law, except for the circulation was over a loop instead of over an area, and it was current enclosed instead of charge enclosed. Now there is a Gauss's law for magnetism, but Gauss's law for magnetism says the magnetic flux is equal to 0, because magnets always come in dipoles. You always have the total magnetic charge enclosed is 0. And since the magnetic charge enclosed is always 0, the magnetic flux for a closed surface is always 0. So we never use that because it doesn't help us. In our in, not our, James Clerk Maxwell's derivation of electromagnetic waves, he did use that. But that was not our purposes. So make sure you can use Ampere's law to go from the circulation to find the current, or from the current to find the magnetic field. Electromagnetic induction. Induction is making current flow. So, well, electromagnetic induction, making current flow. So we had Faraday's law of induction that said the induced EMF is equal to minus n change in magnetic flux divided by change in time. Now, this was not the magnetic flux for a closed surface, so that would have been 0. This is the magnetic flux for a loop. So you have, in this case, a real surface, a real loop with current going through it, or excuse me, not with current going through it, but a real loop, physical loop. And if the magnetic flux changes, it's going to induce an EMF. That's why we use that script E. EMF, electromotive force, or more commonly, voltage. This minus sign is to remind us we have to use Lenz's law. Lenz's law says that the induced EMF is going to produce a current that will try to keep the magnetic flux constant. So if the magnetic flux is increasing in strength, then the induced current is going to flow to make a magnetic field that would oppose the direction of the magnetic field that exists. If the magnetic flux is decreasing, then it'll create a current in the opposite direction to try to supplement the magnetic field. So that's what Lenz's law is. So you have to use the two together, Faraday's law of induction and Lenz's law together, to determine not just the voltage, but also the direction. Transformers and electric motors. Let's start with electric motors. In construction, electric motors are constructed essentially like generators. The difference is, in a generator, in a generator, you put, I think I have this out of place, but it doesn't matter. In a generator, you put mechanical energy and you make a coil rotate in a magnetic field. And yeah, this was supposed to be generators here, not electric motors. That's where the problem is. You put mechanical energy in to rotate a coil, and so the rotating coil in a magnetic field has a constantly changing flux. That magnetic flux changing induces a voltage. And so electric generators, you still have a coil, it's still rotating in a permanent magnet, but now you're forcing it to rotate and you're getting a voltage out. Whereas a motor, you're putting a voltage in, which makes it rotate and you get the motion out. So a generator is just the opposite of an electric motor, fundamentally. What about transformers? Go ahead and say it. They're more than meets the eye. What is a transformer transforming? Besides that, why is it called a transformer? Okay, it transforms electricity into electricity. That's an accurate statement. It transforms from a higher to lower or lower to higher voltage. Has to be AC. Why does it have to be AC?
Because DC can't really change.
That's true, but why?
Because it's constant.
Because this equation right here requires that you have a changing magnetic flux. And a transformer works by taking a primary coil and having current going through it to make a magnetic field. Then you have a secondary coil that shares that magnetic field. But if it's a constant magnetic field, the flux in that secondary coil is constant and nothing's produced. But if you change that magnetic flux, then you produce something in the secondary. And then, of course, we have our important relationship for transformers that, well, V1 over N1 equals V2 over N2. The voltage in the primary divided by the number of turns in the primary is equal to voltage in the secondary divided by the number of turns in the secondary. So you can step up or down just by changing the ratio of N1 and N2. So simple relationship there. And if you step up the voltage, what happens to the current? It has to step down because you can't make extra power. If the voltage steps up and the current stayed the same, you'd have more power. Current has to drop so the power remains constant. Or you can have something that's not perfect and you lose power. Inductors. What's the difference in an inductor and a transformer? Those are pieces of iron in both cases. One of these is a transformer and one's an inductor. Which one's which?
That one is a transformer.
Which means by process of elimination, I wanted to say using inductive reasoning, but it's deductive. The inductor has a single coil. The transformer has two coils. The inductor is a self-inductor, whereas the transformer is a mutual inductor. So the transformer, you put a voltage in on one side and it causes a voltage out of the other side. An inductor, you put a voltage in and it causes a voltage back on the same coil. Because you put a voltage in, you create a current, that current makes it, or you have a current, that makes a magnetic field, but the changing magnetic field creates what we call a back EMF. It creates its own voltage as per Faraday's law of induction. And so we have a voltage drop across an inductor as calculated by Faraday's law of induction. So, of course, you have to have AC for an inductor to really do anything of use because it is storing energy in the form of a magnetic field, and you get that energy back only if the magnetic field changes. So at this point, we got to RLC circuits. Make sure you can calculate the impedance and the reactance. I think I removed the next slide. XL is equal to omega L, XC is equal to 1 over omega C, and the impedance equals square root of R squared plus XL minus XC squared is what that last thing is. Right, so make sure you can calculate those, and then we have Ohm's law works just the same. Ohm's law becomes V equals IZ. That's a Z. So make sure you can use the same Ohm's law, the same Kirchhoff's laws, but using impedance with inductors and capacitors. We have 12 minutes left. We're halfway through. All right, electromagnetic waves. This was a short section. What's Sade? It is a lot. I'm trying to cover the whole semester in a day. So yeah, it's a huge amount. Which is why I'm going fast and talking monotone. James Clerk Maxwell altered only one of the four equations that he eventually combined to describe all of electromagnetism. That one equation he altered was Ampere's law. So it's sometimes called the, I think, Ampere-Maxwell law. And that is, he realized there was nothing to describe where the current enclosed is for a loop. And with a capacitor, you could decide to make where you measure the current so there's no current if you go between the two faces. So he said there's something missing here, and he introduced this thing he called the displacement current. And that displacement current is in the end something that says a changing electric field acts like a current and is going to induce a magnetic field. And so Ampere's law becomes an equation that says changing electric field creates a magnetic field. But we had earlier from Faraday's law that changing electric field created a magnetic field. And so Clerk-Maxwell took the four Maxwell's equations, Faraday's law, of course, and Ampere's law, as well as Gauss's law for magnetism and Gauss's law for electric charge, and combined them to predict electromagnetic waves. And so he had equations, and remember, he went from his first set had about 20 equations to describe all electricity and magnetism, and then he cut it down to 4. And those 4 equations predicted electromagnetic waves, and they even gave it a speed for them, and that speed turned out to be the same as the speed of light. And Clerk-Maxwell made the incredible conclusion that light must be an electromagnetic wave because they had the same speed. It was Heinrich Hertz that actually did experiments to show, yeah, light is in fact an example of an electromagnetic wave. So make sure that you know the order of the electromagnetic spectrum. I put these in order from lowest frequency to highest frequency. They're all electromagnetic waves. Only visible light is technically light because that's the only thing we can see with our eyes. So we shouldn't call ultraviolet light light. We should call it ultraviolet radiation.
Are those in the right order?
Yes. But they're all electromagnetic waves. You should be able to convert between frequency, wavelength, and photon energy. Remember, wavelength times frequency is equal to the speed for any wave. And for photons, energy is equal to h times frequency. So you should be able to do those conversions simply, be able to identify the parts of the spectrum. What kind of radiation is dangerous to us? What kind of electromagnetic radiation is dangerous to us? Okay, gamma, why? Next person.
Frequency.
Okay, its frequency is high, and if it has a high frequency, it has photons with a high enough energy to ionize molecules. So when you get up above around 2 electron volts, you can start doing ionization. Above 10 electron volts, you're going to ionize things in your body. Well, that's starting to get dangerous. So somewhere around 200 nanometers wavelength is where you're getting into dangerous, because it's surely going to ionize things in our bodies and cause damage. Light. I think most people, like me, breathed a sigh of relief when we got out of electricity and magnetism and went to light. Light is something we see by definition. And because we see it, it's easier for us to have a feel for what it's going to do. And so we talked about using the ray model of light. Make sure you can explain why we should use ray models and do ray drawings, things like using the law of reflection or Snell's law, how an image is formed, where a mirror is going to form its image, those kinds of things. Make sure you're familiar with Huygens' principle on, any point in a wavefront can be treated as a source, a point source for new waves, and how that is used to build up our knowledge of geometric optics. And of course, specular reflection. What's a more common word for specular reflection? Mirror. Specular is a mirror-like reflection. Diffuse is not. Diffuse reflections occur because you have a rough surface. And so for diffuse reflections, light goes everywhere. If you look at somebody's clothing, you're seeing a diffuse reflection off of that because the clothing is not smooth. It's got a lot of variation to it. If you look at Toussaint's jacket there, you see some glare off of it. That tells us that we have some pretty smooth portions on his surface of his jacket, so that we're getting a specular type reflection rather than a diffuse type reflection. be able to do your geometric drawings to construct images from mirrors or lenses, or be able to do them with equations. So you should be familiar both with 1 over f is equal to 1 over distance image plus 1 over distance object, as well as how to use your parallel ray, your focal ray, your vertex ray, and if it's a mirror, you can use a center ray if you like. I always require 3 rays on a diagram to make sure that you did it right. 2 rays are always going to meet. 3 rays, if they meet the same place, that's a better prediction of doing it right. So make sure you can do these things either way. Describe if it's inverted or upright, magnified or diminished. I got 5 minutes left. I might make it. In vision, make sure you know the pieces of the eye and what they do. And so I put here a list of some of the basic things. The cornea focuses light. The lens accommodates light. I skipped one in between. What does the iris do? Okay. I didn't hear what you said. I thought you said interacts with people. It took me a minute and then I realized that's not what you said. You're thinking, why is he looking at me that way? Okay, the iris is what adjusts the pupil. It makes the pupil bigger or smaller. The pupil is the hole in the iris, and so it controls the amount of light that comes in. The lens does accommodation. What's accommodation? It changes its shape for accommodation. It's allowing us to have a variable focus. If we didn't have that lens, we would just have a fixed focus. Then we have rods and cones on our retina. The rods just see light and dark. The cones see colors. What are the 3 primary colors for cone vision? Yeah. So that's why those are 3 primary colors of light, because that's what we have cones to see. One cone that's most sensitive for red, that's more sensitive than the others for red. One that's most sensitive in green, one most sensitive in blue. Then we have the microscope and the telescope. Microscope and telescope, they're both for viewing things, but microscopes are for viewing small things that are near. Telescopes are for viewing large things that are far away. Both of them increase the angular size of what you see. So the angular size is how big of an angle the light rays make with your eyeball. And a microscope takes something that you bring as close as you can, and you get the angular size. It allows you to make it a bigger angle by making an image that's bigger, still far enough away for you to see. Make sure you remember the difference between accommodated and unaccommodated viewing. Accommodated viewing is when your lens is working hard. It allows you to add just 1 to the magnification. A lot of people seem to not remember that n was the near point in the equations that had to do with microscopes and telescopes. What's the near point for a human eye? We talk about it as if it's 25 centimeters for everybody. That's just a standard. It's obviously different for everybody. Now we have our vision problems: myopia, hyperopia, presbyopia. Which one am I far more likely to suffer from than the rest of you? Presbyopia. Because I have this presby thing. What does that mean? I'm old. Sad truth. Myopia, commonly called nearsightedness, which means you can see things near just fine, but you can't see things that are far away. Hyperopia, commonly called farsightedness, because you can see things that are far just fine, not things that are near. Make sure you understand, in terms of curvatures, what the problems are for those two, and how you fix it with lenses. Remember, I think it was Diksha's glasses that we used. We had Diksha come up here, and we measured her far point to be about here, and then we calculated her prescription. Now, you're not going to take that calculation to the eye doctor because we were pretty sloppy in our calculation and work. But that's essentially what the eye doctor is doing, measuring what your near and far points are, and then finding lenses that will fix them. What kind of lenses does somebody with presbyopia need? Bifocals, or the newer day we have the gradient ones that you just adjust your head and you're focusing for different distances depending on your head angle. Yeah.
Okay, so presbyopia is one that hardens the lens, right? And
Presbyopia.
so if LASIK surgery don't some of them replace the lens, so couldn't they just replace it?
Lenses, as far as I know, are never replaced. The lens is back behind the iris. The cornea can be replaced, and the photorefractive surgeries are reshaping the cornea.
Because I saw the surgeries and they pull out the clear lining deal and then they plug in something else.
There are corneal transplants, and I think they even have artificial corneas, but still cornea, not lens.
Okay, I'll have to look at it.
The cornea is lens-shaped and has a lens job, but the lens is the second one in there. Okay, that brings us past our time here. Almost got through the last exam. Well, question, Michaela.
Since this is so much information, if we all kind of do not as well, do you scale final, or is it whatever?
It will probably be whatever you get. It's the scores tend to track across all the exams. I scaled the first two this year because we had some difficulties. Alrighty, so when do I see you next? Yeah, I don't know, never. If you're coming to take the final on Tuesday at 1 p.m.